Welcome. Today we're going to be talking about the existence and uniqueness of solutions to differential equations. So in particular, we're going to be talking about first order equations. And so of the form like this. We're going to be talking about first order initial value problems, which we all know what those are now. So let's write that down. So we're going to write it as dy dt is equal to f of t comma y. And then along with it, we have some sort of initial condition, y at some time a is equal to some value b. Or rather, we could write this also as just the solution. We want a solution that goes through the point AB in the plane. Okay, so the question then is, and this is the question we want to answer is, if we're given this dE, the question we want to answer is, does the IVP, this thing right here, have a solution and is it unique? Okay, so what do we mean by have a solution and being unique? Is that, i.e., we want to find, or basically we want to know. We might not be able to find it, but we want to be able to know if there is a y of t such that y of a equals b and y prime equals f of y, or t comma y. All right, so I'm just rephrasing things here, but that's the idea. So if I were to draw a picture of this, what we're talking about is, here is the ty plane. Let's say in there somewhere I have a point a comma b, and I'm looking at that point and I'm given this differential equation. Is there some function that passes through that point? And it might, who knows what it does away from that point, but somewhere nearby this point, can we find a y of t solution, this curve y of t, that satisfies this differential equations? So this differential equation. So I'm going to kind of elaborate on this question a bit and kind of narrow down what we mean. So what is unique about this first order IVP? And the question really is, so this part right here, dy dt, is always the same, but really what the unique part that makes this differential equation a specific differential equation is the fact that we have an f of t comma y. This function is what we're going to be looking at. So if I was going to rephrase this question, so I'm going to rephrase it as, what conditions on f of t comma y on the point a comma b or nearby, and I'll explain what I mean in a second by nearby. And what I mean is, there's some conditions, some properties about f guarantee a unique solution. So clearly, obviously, if f doesn't even exist at the point AB, then this equation makes sense. This equation would make no sense. So let's see if we can basically analyze something like this. All right, so I'm going to go to a new page now, and we're going to talk about. Let's set up this problem again. So it turns out this question we have, the answer, of course, is yes, and the result is there is a theorem. Okay, so here's what the theorem states, and so this is the theorem on existence and uniqueness of solutions to the IVP dy dt is equal to f of t comma y with the initial value y of a equals b. Okay, so I want to know if this has a solution. And so the hypotheses of the theorem are as followed. If, and I'm going to state this in a numbered list of conditions, f of t comma y is continuous in some region, I'm going to call this region R, around the point A comma B, and 2, an additional condition, the partial derivative of f with respect to y is also continuous. In R, then there exists a y of t, I should say a unique y of t such that or I should say that solves the initial value problem. Okay, so what do we mean continuous in some region R? And we need to also elaborate on this solution a bit more. There exists a y of t that solves the IVP on some interval I, on some interval I, and I got to explain this a bit more. So we need to set up, I'm going to draw a little picture here. So if I have my point AB, when I mean a region R, I mean some sort of rectangle that I can draw around AB, where the edges of the rectangle, and I'll call this rectangle R, the rectangle, the point AB can't be on the edges of the rectangle, it has to be inside of it. Okay, and we want this, and this rectangle, it could be any rectangle, but it just has to be surrounding my point. So when we mean region R, we really mean as a neighborhood. Okay, so and on some interval I, and I need to clarify. So this rectangle I can write as T1, T2, and I could also have y boundaries Y1, Y2, such that, of course, that T1 is less than A sorry, T1 is less than A and A is less than T2, and also that Y1 is less than B, which is in turn less than Y2. Okay. All right. And so this interval I, which is going to be an open interval contained in the interval T1, T2. What I mean is the interval is like this. So this interval I, so A is an element of I, then I, so that's my element symbol. That means that A is inside of I, and it's a strict subset. It could be a strict subset of T1, comma T2, this interval. All right, so that is the formal theorem. So what we're going to do then is we're going to go over a few examples of how to use this theorem. Okay, so again, the question will always be, is there a unique solution to my differential equation? And we're going to go through several examples where we choose different f functions that we're going to go through several examples and see if we can test condition 1 and condition 2. See what we mean by the interval I and what we mean by this region surrounding I where continuity has to exist. All right, so let's do that. So first of all, before we get started, we need to remember what continuity means. Of a function g of y, or sorry, t comma y means that there are no, I should say on R. I'm going to back up here a bit. I want to be very specific in my language of a function g of t in some rectangle that there are no jumps jumps in G for either t or y in any of the t or y directions. So again, we have this rectangle, and again, it just has to be a rectangle. It could be very small. It just has to enclose our point A comma B. And this function, it just means that as I move values through this space, this function can't jump. It has to be, the values as we go through this rectangle can't have any discrete jumps as we're moving through it. Okay, so that's the idea behind what we mean by continuity. All right, so now let's get to a specific example of a function or of a differential equation. So let's start with the differential equation. dy dt is equal to y squared. Okay, and we're going to be looking at the point time equals 0 is equal to let's try 1. Okay, so with this particular DE, this is an IVP. So I want to know again, is there a y? Okay, is there a unique solution to this? So let's go through the hypotheses of the theorem. Okay, so again, first, f of t comma y is actually just a function of only y. There's no t in it at all, and it's equal to y squared. So we can see right here that this is, of course, continuous everywhere. In the ty plane. Okay, now let's go on to the next condition of the theorem. I need to take the partial derivative of my f with respect to y, which of course is 2y, and of course the same thing is true. This is continuous everywhere in the plane. Because both things are true, we conclude there is some interval of time around t equals 0 where y of t is unique, and it exists. Y I should say is exists and is unique. Okay, all right. So let's actually, now we haven't learned how to solve this particular differential equation yet, but in fact, I'm going to just provide you with the solution. All right, so it's not going to come from any particular method, but I'll just give you the solution. The solution is 1 over, it's going to be 1 over 1 minus t. All right, we can actually check that as a solution. So dy dt, that's going to be equal to negative 1 minus t to the negative 2 power times negative 1. That's the derivative of this function. Right, so that becomes, of course, 1 over 1 minus t quantity squared, which is actually y squared. So certainly this is the solution, and also it is a solution to the initial value problem. If I put y of 0 in there, that's because 1 over 1 minus 0, which is equal to 1. Okay, all right, so that looks good. This equation has a a nice solution. Okay, and it's unique. All right, so now let's go to an example where maybe we want to break something down here. All right, so let's try doing another point. Let's try doing another. So now we're going to do another example. We're going to do dy dt is equal to 2y over t. All right, so that's my f of t comma y. All right, so again, we're going to go through the conditions of the theorem. I'm going to be studying what this f function is. So clearly, it is continuous except at t equals 0. So t equals 0 is a problem, okay? So whatever we do, if I draw out my rectangle has to be away from 0. So whatever my point AB is, it better be away from 0 because t equals 0 is a problem. That's off limits. Okay, 2. Clearly, partial of f with respect to y is just going to be 2t. And of course, we have the same problem. Okay, so it provided this function, it provided this, the IVP is provided our initial condition is our point there is away from t equals 0, we should be okay. We have continuity. All right, so let's check some examples. Let's look, and it turns out that if I write down y of t, so again I haven't actually found out how to get this solution, but I will say y of t is equal to c times t squared, where this is a free parameter. And this is a solution, so we're going to check that. So if I go dy dt, that's going to be equal to 2ct. Okay, and clearly if I look at this right-hand side, I go 2, and then I put a ct squared up there. That's my function of y, and I divide by t. I get 2. I want to ask, are these things true? That is, of course, 2tc. So the two match up. So this is actually a solution. All right, so clearly this is a unique solution, and I can draw out what these unique solutions are. Each one is a unique solution, and it goes like that. They look like parabolas. But what if I take time going towards 0, and I'm going to take it from the positive side? You see all of the solutions do kind of come back, and they start getting closer and closer to each other. And of course, that's the point where we have problems. So there seems to be a solution that passes through that point 0, but notice that at that point, solutions are non-unique. At t equals 0. All right, so so those are some examples of solutions that break down. One of our conditions, one or two of the conditions will break down, and although we may be able to find a solution, we can't find a solution that's necessarily unique. Okay, so that's maybe different c values here. Okay, all right. So now let's do one more example. Let's talk about now. Let's talk about dy dt is equal to 2 square root of y. All right, and now we're going to take the IVP. Y of 0 is equal to 0. All right, let's check our hypotheses. So f of y, in this case there's no t, is equal to 2 square root of y. It is continuous at y equals 0. But note, it's not continuous for y less than 0. In fact, this function doesn't even exist. It can't accept negative values. So if I look at, I can't form a rectangle around it. So at y equals 0, if I have that right there, so I'm looking at this point right there, I can't put a rectangle around it that surrounds it. It's always on the edge of the rectangle. All right. So there is no neighborhood around y equals 0 where f of y is continuous. Okay, all right, and of course we can also look here at 2 just for fun, and we see here that that's equal to 1 over square root of y. Oops, y, and of course, and this of course does not even exist at y equals 0. So we have some real problems here. So now let's actually check solutions. So what we conclude then is that there is no guarantee of a unique solution. Okay, the question then is, are there solutions? And it turns out, yes, there are solutions. Let's try some. Okay, it turns out that the function, let's try a particular example. Let's try y is equal to t squared. All right, is this a solution? Of course, dy dt is equal to 2t. All right, and if I look at square root of y, that's equal to t. All right, so so if I make a 2 on there to be with the thing here, that of course is 2t, and clearly that's a solution. All right. So if I draw around here, I can actually put that solution, y is equal to t squared. That is a solution. So even though our theorem could not be used, the hypotheses of the theorem did not hold, I still did find a solution. But now let's look a little closer. Now I'm going to try, so I tried this, and I found that was a solution. Now I'm going to try another solution. Y of t is equal to 0. Of course, that is also a solution to this equation, right? And so it turns out then I have this solution that emanates from 0, but then there's another solution here. Y is equal to 0. That is also a solution. And you see, that's that non-uniqueness coming into play. So clearly, there are solutions, but they are not unique. So again, this theorem can guarantee existence and uniqueness of solutions, but it really doesn't tell you if a solution doesn't exist. And it may be true that a solution does exist, but it's simply not unique, as this example shows. All right, so one last thing I wanted to cover, and I just forgot to cover it. When we go back to that my original example, dy dt is equal to y squared. And of course, we found out that solution was y of t is equal to 1 over 1 minus t. You note here that this solution exists, and the IVP, of course, was y of 0 is equal to 1. But clearly, it doesn't exist forever. Even though this is continuous everywhere, and f df dy is also continuous everywhere. Note that y of t equals 1 over 1 minus t does not exist for all times. In fact, as t goes towards, if t goes towards 1 from the negative side, y diverges to infinity. Okay, so again, let's now look at this carefully. So I have this solution that goes like this. And at t equals 1, it diverges to infinity. So even though my function f here was continuous everywhere, and its partial derivative was continuous everywhere, the interval of existence is some, around the point is whatever it is, but whatever it is here, it's some negative value. We'll say just -1. It goes all the way to 1. All right, so this is arbitrary here, but that is a strict. The y of t function exists, but it doesn't exist for all times. It only exists on this open interval that is less than 1, because at 1 we clearly see there is a divergence. So that's another example of a thing that can happen with differential equations. If I give you an initial condition at a point, I only am guaranteed a solution nearby that point. It may not exist for all time going forward or backward or some scenario like that. We're only guaranteed a solution for a little while. And that's why we always talk about that interval I. Anyway, I hope this gets you some clarification about whether or not a differential equation has a solution, and there's a specific way to test your differential equation to see if it does. All right, thank you very much.